Hey guys, BuildZoid here, and today we're going to do an introduction to transient response in motherboard and GPU VRMs. So in our case, we're going to be talking about the buck converters on your GPU, so that's going to be like vCore, memory power, anything that needs to provide more than like 3 amps is probably going to use a buck converter, single phase or multi-phase. For this video, I'm using this right here is a heavily simplified two-phase voltage regulator, so we've got phase 1, phase 2, right? We've got our capacitor bank, and we've got our controller over here, and then we have our CPU. Where was I going with this? So, yeah, we'll be talking about just for VRMs. Now then, transient response is a term that can be applied to, as far as I'm aware, any control system, but I obviously only care about VRMs, or at least for this video, that's the only thing I care about. So transient response is how our voltage regulator responds to a transient, and that's not very helpful, so it's how does the voltage regulator respond to a change in load, which is also commonly referred to as current demand, which is actually very misleading if you don't know anything about electronics and CPUs and VRMs, because you tell somebody it's how your VRM responds to current demand, and they start thinking, oh, so the CPU goes over to the controller and starts making demands about how many amps it's going to get. So, your CPU will go up to the controller and say, hey, could you please give me 100 amps? And this does not happen at all. CPUs do not work like that. VRMs don't work like that. There is some basic warning systems that the CPU can use to talk to the VRM, like it can tell, hey, we want to go into a low power state or high power state, that kind of thing, which is actually more commonly used on GPUs than on motherboards. On motherboards, normally the controller just has to deal with whatever the hell the CPU decides to do. And for the purposes of this video, the CPU will be simplifying it down to just being a very fast, very low resistance resistor. So at idle, our CPU will basically look a lot like a 0.1 ohm resistor, which is not actually that far off, because at 1 volt, 10 amps, that would be, at 1 volt, 0.1 ohms is going to pull about 10 amps, which is about 10 watts of power consumption. So actually not about, that's exactly 10 watts of power consumption, which isn't that unrealistic for a modern CPU at that kind of voltage and idle. Well, depends what CPU you're looking at, but I'm sure if you look hard enough, you'll find a CPU that pulls 10 amps at idle, so, and at roughly 1 volt. And then for full load, the CPU is going to look like a 0.01 ohm resistor, which at 1 volt would be 100 amps. So this right here is, roughly 10. This right here is roughly 100 amps, and this right here is 10 amps again. And so the obvious issue here is that the CPU never actually goes over to the controller and says, hey, I would like 100 amps. The CPU just kind of goes low resistance, and the controller is left to deal with the consequences of that. Because our VRM, the way that we do the voltage conversion is we rely on these lovely components called chokes/inductors. I like to refer to them as inductors, as it's like, if you like, one thing that really annoyed me when I first got into computer hardware was trying to figure out like what electrical component is a freaking choke, because nobody, like, it took a while to figure out that it just means inductors, and that was many years ago. If anybody is just don't be worried, many years ago. So anyway, yeah, we rely on these inductors to do the voltage conversion, and the problem with this is they don't really do current, like changes in current, very quickly. That's just not a thing they do. So worst case scenario for this transition right here from idle to load, which is where you transition transient, right? You can see the connection there. Though I'm not sure that's actually the origins of the word, so don't quote me on that, but makes sense to me, right? So our transition between idle to full load is called a load insertion transient, and we're going from, low resistance to even lower resistance in the span of potentially a couple microseconds. CPUs can go very quickly between doing absolutely nothing and doing everything at the same time, and doing absolutely everything, right? And that's kind of a real problem. So, the resistance drops very quickly. And the worst case scenario for this load insertion transient to occur in is right in between high pulses on the PWM lines. So these are the PWM signals for, phase 1 and phase 2. And as you can clearly see, our transition happens starts right here, right? It happens in this area. And you can see, there's no high pulses right there. And the reason why this is a real problem is because in between pulses, all of the current flow going through our VRM, or, well, the current flow through our inductors, we're just going to pretend mostly that the capacitors don't exist, because there's a lot of things happening at the same time, and most of them are related to the capacitors. So anyway, so in between high pulses, the current flow through our VRM is we're going to have 5 amps flowing through each of our inductors on average. It's not actually going to be 5 amps, but just for simplicity's sake, 5 amps. In reality, this would be like a declining amount of current, like it would be a falling amount of current, and then and rising amount of current when the high side turns on again, but that's details. So we have this 5 amps of current flowing through each of our inductors, and the way this current flows is it flows from our inductor into the CPU, through the ground plane, back through the low side MOSFET, and back into this inductor. And this 5 amps of current flow is entirely being produced by the magnetic field that we charged up in the inductor when the high side MOSFET was turned on. So the problem right now, when the CPU goes from relatively high resistance to low resistance, is that there's no extra energy. Like, there's just nowhere to source more current from. Both of our inductors are essentially configured right now to provide 5 amps, and until we do something with until you turn on the high side MOSFETs, they will continue to provide only 5 amps. So in the meantime, what's actually going to happen is, and if we didn't have a capacitor bank, as soon as our resistance drops like this, our output voltage would drop with it. And so, for 0.01 ohms, assuming that you're pushing a combined current of 10 amps into a resistor of 0.01 ohms, the voltage drop across the resistor is going to be 0.1 volts, which if that was a CPU, it wouldn't run. Because that's way too little voltage. CPUs do not run on 0.1 volts. So the solution to the problem is our lovely capacitor bank here, because all of the current that we can't get out of our inductors, because they just don't work that way, we can get out of our capacitor bank, at least temporarily. So for a little bit, we're basically going to have 90 amps, not really, but pretend like it is, because it's simpler to just pretend that it is 90 amps. But essentially, all of the current that we're missing, right, that our inductors aren't able to provide, well, we can grab it from our capacitor bank for a little bit. The reason why it's only for a little bit is because the capacitor bank, it does store energy, but not infinite amounts of it. And that means as we pull current out of the capacitor bank, the voltage does keep falling. Well, still falls, but much, much slower than if we didn't have a capacitor bank whatsoever. So our voltage starts to fall, and how quickly it falls is basically dependent entirely on how many capacitors you have. If you have more capacitor, like the better configured your capacitor bank is, the less steep this is going to be. Right? So if you have very few capacitors and they suck, it's going to be very, very deep. It's going to be very steep. And if you have a lot of capacitance and it's also very well, connected to the CPU, you're going to have a much slower decline in voltage level. Eventually, our lovely controller over here is going to notice that our voltage is no longer 1 volt. And the thing is, there has to be a certain margin of, don't do anything yet, because you can't have the controller freak out over every 5 millivolts change in voltage. Because the CPU, even at idle, it's actually constantly varying how much current it's pulling, but a very small amount. So the voltage level on our power plane is never really going to be a straight line, and then you also have the switching noise from the VRM itself, so you don't actually want the controller to freak out over every small decrease or increase in voltage, because that would cause major issues. But eventually our controller is going to be like, wait a minute, we are way off where we're supposed to be, right? We're aiming for 1 volt here. This, say this point right here, it's not 1 volt. That's like 0.93 volts or something. And so at this point, our controller is like, okay, the voltage is falling, and it is going to make an alteration to the PWM signal that essentially, and this is going to be like this adjustment to the PWM signal is going to take some time to propagate to your high side MOSFET, which is why you'll notice that like, you know, if we say the VRM, like you could also have the controller notice like the gap between when the controller notices and when the high side MOSFETs actually turn on. Well, it'll depend on the design of the VRM. But yeah, so eventually our controller makes the PWM signal adjustment, and essentially what it does is it just tells both MOSFET, in like this adjustment I've drawn is not realistic. It's not very realistic. There are some controllers that can do something like that. There's lots of controllers that don't do anything like that. In fact, and depending on how basic depending on the controller, there's going to be a very different adjustment to the PWM signal. But for convenience sake, I've just drawn a scenario where our controller is just super clever and immediately figures out how long it needs to turn on both high side MOSFETs on for to, you know, bring our voltage level exactly right back up to where it's supposed to be, which is not realistic because normally the controller will miss a little bit. It'll also not necessarily do something like where it just gives you two big fat high side pulses. There are a bunch of different ways this is going to be done. But here we're just going to go, you know, this is nice and simple. So it turns on both of our high side MOSFETs. And so now we finally have 12 volts being applied to the switch node. So we can start increasing the current from 5 amps up to 50 amps in both of our phases. And, you know, that is going to then charge up some of that current's going to go back into the capacitor bank. So actually it's going to be 50 amps in quotation marks, not actually 50, but roughly 50. So some of that's going to be used to recharge the capacitors because the voltage just fell off a cliff. And a lot of that is just going to go straight through the CPU. And that's going to bring our voltage level back up to where it's supposed to be. Yay, our controller is super smart and not realistic at all. Because, like, this normally just does not work this well. And also a lot of controllers won't actually do anything like this at all. But for convenience sake, I think, you know, like the control will do something that you'll see in the PWM signal, but I just went for easy option to draw. And, you know, then we're back up at our correct, like the target voltage level that we were aiming for initially. And this whole thing right here, this is called undershoot. And undershoot is literally just, the funny thing is, once you include things like load line, which I'm not sure, I think I'll do load line as a separate video, and I'll also do a separate video talking about various things that can be done to improve transient response as well. So anyway, but this right here is called undershoot. The transition is called, you know, a load insertion, and load insertions cause undershoot. That's what they do. And the deeper this, you know, the further away our minimum voltage here, right? This is our minimum voltage, min. The further away that is from our target voltage, which in this case is 1 volt, because we are running a VRM with no load line whatsoever. So with this 1 volt target voltage, we here have 100 millivolts of undershoot because that's a 100 millivolt gap. So that's 100 millivolts of undershoot. Another easy way to think about it is, well, an alternative way to look at this is just like if you're measuring a voltage regulator that's running, you know, and you hit it with a transient load, whatever minimum voltage you hit, like the lower the minimum voltage it hits during a transient, the worse the transient response is, right? Good transient response is having a very small deviation in the voltage. A bad transient response is, well, you know, potentially a very large deviation, and then it might take forever to recover as well, and you know, so that's a load insertion transient, and that's your undershoot, and it's entirely caused by the fact that, well, we just can't pull, like, you just can't force the inductors to provide a bunch of current until you turn on the high side MOSFETs. And even if you have the high side MOSFET turned on, you might have to do something like a PWM pulse extension or just something. You're not gonna get, like, even if you know, if I pushed this transient back to here, right, to actually align with this pulse right here, well, initially it might, it might start out relatively mild. So initially it might fall a little bit, and then it would still, fall down fast again, because um, the current flow through the inductors wouldn't be like, it wouldn't be getting ramped up for long enough to go all the way up to 50 amps. It would maybe, it would increase, like, and it would also only be through one phase at the time, not both of them. So anyway, so that's a load insertion transient, and then we get the other end of that. So after, our load insertion transient and our VRM's response to that, eventually we go back to, standardly spaced PWM pulses on our two-phase. So, you basically have the reason I have these marks down here is to indicate when every pulse is supposed to happen, and they're supposed to alternate between the two phases spaced by 180 degrees. So that's why, you have the gap where it's 4 squares to this side and 4 squares to this side as well, right? 4 here, 4 there. It also conveniently works out to be a 10% duty cycle, which I could have said that this is actually aiming for 1.2 volts, but then, 10 amps and 100 amps would be like 12 and 120, and it makes things unnecessarily, like it makes the numbers uglier, in my opinion. Anyway, so then we return back to steady state operation. Everything is great because we're back at 1 volt. And then eventually our CPU stops doing whatever it is that it's doing, and it goes right back up, it goes from very low resistance back up to just low resistance. Now we have the opposite issue, because we've just, charged up our inductors to push 50 amps through them, and they really want to keep pushing 50 amps through no matter what. And so let me just erase all of this. Right, so now we have our 50 amps flowing through each of our inductors, and most of the time this, and during steady state, we'd have that just flowing through the CPU and everything would be golden. And then the CPU suddenly decides to go high resistance, and now this 50 amps has nowhere to go, kinda, assuming, we're just going to temporarily pretend the capacitor bank didn't exist. So if we didn't have the capacitor bank, well, in order to keep pushing 100 amps through a 0.1 ohm resistor, you'd need like 10 volts. So the voltage is going to jump really hard, because there is some inefficiency in the inductors that are not necessarily going to go all the way up to 10 volts. Yeah, they're going to, you're going to get a massive voltage spike, and that's just going to end the CPU immediately. So we need to put all of this energy that's in these inductors that has, kind of nowhere to go somewhere. And that somewhere is, of course, the capacitor bank again. It's great. And we can just, when we don't have enough energy when on a load insertion, we don't have enough energy, pull it from the capacitor bank. When on a load release, we have too much energy in the inductors, dump it in the capacitor bank. And so a lot of the unnecessary power just gets dumped into the capacitor bank, and then some of it obviously keeps going through the CPU because it's not infinite resistance. It's 0.1 ohms, so you're still going to have some current flowing through it, but a lot less, right? So you're totally going to have 10 amps flowing through the CPU, and it's not actually going to be 10 amps because the voltage level is going to go up, and the rest of that's going to get dumped into our capacitor bank, which, that'll be the other 90 amps. Right there, in quotes again, because we're totally, I'm simplifying everything heavily, but the rest of the current's going to get dumped into the capacitor bank. The capacitor bank is not an infinite, not an infinite source of energy. It's also not a black hole for energy, so that's why we still get a voltage increase, but it's much smaller and takes much longer than if we didn't have a capacitor bank at all. And eventually, somewhere along this voltage increase, the controller will be like, wait a minute, that's not 1 volt. Blank out a bunch of the pulses, right? So we were supposed to have a pulse right here, but that's right in the middle of our load release transient, so canceled. And this pulse over here, well, do you see what the voltage level is for this part right here? That's a lot more than 1 volt. The last thing we need to do is put more energy into the output when we already have unnecessary, the capacitor bank is already charged to way higher voltage level. We don't need to put more energy there. So we cancel that pulse as well. And then eventually our voltage level drops to appropriate levels, and we can go right back to steady state operation where you have your regularly spaced 10% PWM pulses. And that right there is load release overshoot, right? Like this right here is a load release transient, and this is overshoot. And overshoot, again, is relative to the voltage you're aiming for. So here we're always aiming for 1 volt. So we have 100 millivolts of overshoot, we have 100 millivolts of undershoot, and so we have a min and max voltage, like target voltage 1 volt, min voltage 0.9, max voltage 1.1 volts. If we had a VRM with better transient response, we might have something that looks like this. Or if we had a VRM with worse transient response, we just have, bigger spikes instead. So that's all there really is to like the basics of what is transient response. That's all it is. It's just like measuring how the VRM manages to deal a load transient with a load transient. And the main issue with load transients for buck converters is just like your inductors, like now you might be sitting there like, why do we use inductors if they cause all these issues? We use inductors because this is the most efficient way to do DC to DC voltage conversion. If you like, there are ways to convert voltage with better transient response. The unfortunate downside to a lot of the other voltage regulation methods with better transient response is awful efficiency. So this right here is used because if you have a 100-watt CPU, the last thing you really want is also like a 200-watt voltage regulator or something stupid like that, right? Again, depends on what exactly you're trying to, like how exactly it's designed, but you can get very, very inefficient voltage regulators depending on just how basic you want to make the design. And buck converters are extremely efficient, right? We can have VRMs with upwards of 90% efficiency, and there's just not really any other way to get that with not really any other way to do that other than relying on inductors. And then having to figure out a workaround for the fact that they kind of suck when you have a transient going on. So, yeah. What else did I want to mention? Right. The reason why this right here is a concern and this right here is a concern. So this is simple. If the voltage level gets high enough, right, dead CPU. Now, I say high enough. I don't actually know concrete values for how much overshoot is too much overshoot for any CPU architecture. I have no idea. You'd have to ask like Intel or AMD or Nvidia, like somebody who actually makes designs the chips, and or TSMC. TSMC would probably have the answer as well. It's just like how much overshoot are these chips able to tolerate? They'd have an answer. I don't. But generally speaking, I'd say so much like overshoot is not really a concern when overclocking. At least, well, I wish I had proof for that, but it's just, it just doesn't seem to be much of an issue. It might be, and all of the like maybe there's like the thing is I'm not aware of people reporting that their overclocks on crappy motherboards cause their CPU to degrade faster. It normally just blows up the motherboard if the motherboard is bad enough. And at that point, it's just like, well, it blew up the motherboard, so obviously the CPU didn't care. Like you'd basically need to run like very edge case overclocks on lots and lots of CPUs, and then some of those CPUs would have to be subject to voltage regulators with bad transient response, and some of them would be with good voltage regulators with good transient response, and then you'd have to, take the statistics of which ones degraded how much in how much time, and at the end of that, you'd probably find that the VRM with better transient response degrades CPUs slower than the other one, but by how much, I have no idea. And also it also depends on your absolute voltage levels, right? Like if you're at a very low voltage and then your overshoot is really bad, well, it's still like the peak of that is still going to be could be relatively low relative to what's actually dangerous to the CPU. So, yeah, but this is concerning from a reliability perspective for longevity. This right here, on the other hand, limits your maximum frequency. Right, because if your CPU is because the thing is, I have a very clean transient, but you can have transients that look like well, you can have workloads that your CPU and GPUs are especially bad about this, but you can have CPU and GPU workloads that look like this, and then your VRM just like, and then having your VRM not keeping because the problem here is that you're actually at a relatively high amount of load, or you could have something that bam, and you just get a couple spikes and then it's full load, a couple spikes, full load. And The problem with this, of course, is that if your VRM has a bad transient response, then when you're under full load, your actual operating voltage is going to be really low, right? Like so the minimum, like the voltage necessary, like you need the same level of voltage for the frequency, basically, no matter what, right? Like at a certain amount of load, you need the voltage to stay constant. If the voltage is significantly lower, then your maximum frequency is reduced. So if you had a voltage regulator that instead of doing what like here we have 100 millivolts of undershoot. So let's say on this VRM we can do a I don't know 900 megahertz overclock, right? Then on a VRM that does this, just doesn't have any undershoot at all, which is impossible, but let's just pretend, we might be able to do 1,000 megahertz instead because our voltage never dips, ever. And that's why you would want good transient response. It basically means you can overclock more. And admittedly, like the differences so far in my testing, the differences between good motherboards at most is like 20, 30 millivolts. And that just doesn't like that's just not a very big difference. Like yes, you'll notice that, and essentially like if you have a motherboard that has 30 millivolts less undershoot, it means you can run the same overclock with a 30 millivolts lower voltage, but it's just like it's not really that big a difference. But there are some motherboards which are exceptionally bad, and on those you need like 100 millivolts or 150 millivolts more voltage to hit the same clock speed as on a better motherboard, because your undershoot on that motherboard is like down here somewhere, right? And it's just like, well, that's bad, right? Like your voltage regulation is completely out of whack, and therefore your overclock is horribly unstable. Also, it's worth noting that all of these events happen on an extremely small time scale. Your CPU can go from idle to full load in a matter of microseconds. This right here is also measured in microseconds. So the problem with this is, of course, you can't see transient response in software, monitoring software, like your hardware info, your CPU-Z, your hardware monitor, which you shouldn't use because it's terrible. But all of these monitoring utilities, they will not pick up on transient response. They'll not pick up on undershoot or overshoot. It's not possible for them to pick up on it. It's way too fast. You can't see it. So anyway, that kind of covers the basics of transient response for buck converters. It's caused like there are design alterations that I'm going to talk about in another video that can be done to try improve this and improve that. There's like also a bunch of fancy control tricks that can be done, which I'm not sure I'm going to talk about because they're very like a lot of them are extremely like proprietary to the various voltage regulator manufacturers. So it's just like they don't really want to give you a lot of details on how like what exactly it looks like when it's active. And a lot of the time they're not necessarily enabled because they can cause more issues than they solve depending on what exactly, like, because if you have a nice neat transient like this, then sure. But if you have something very messy, then it's like having the VRM go, if our VRM decides that it's going to inject this massive PWM pulse right now, and then our load just goes, like that, we're screwed. Like, our voltage, like, instead of having this nice ramp up to where we're supposed to be, we'd get something stupid like that, right? Where it's just like, well, the response came, it's a bit like the voltage regulator just, it totally missed the window. It just made a massive mistake. And that's also part of the reason why you don't actually see something like that on real voltage regulators and why I said this is for convenience. There's other things that they'll do to improve transient response. They won't try to make one pulse adjustments like this. But this is just the convenient way for me to draw this out. So, anyway, yeah, hopefully this covers enough information that you can sort of watch the oscilloscope measurement videos I've been doing for motherboards and GPUs and that kind of thing, and they'll actually make sense now. Because basically what we're looking at is the ability of the voltage regulator to maintain output voltage in spite of the fact that the inductors really, really hate changing output current, like really hate adapting to the changes in the resistance of our CPU, right? Like, or more like the inductors just don't adapt, and we need to turn on the high side MOSFETs in as quickly as possible and as accurately as possible, because that's the other thing, right? If you turn them on for too long, you cause more problems than you started with. So that's it. That's transient response. Man, this video has been so difficult to shoot. So hopefully you liked it, and it'll make you subscribe and share the. Actually, I don't even know that I want people to share this video because I still really don't like it. Um, but yeah, like I'm not sure that, like, I don't think it's possible to try simplify this any further. And like my main personal complaint is this right here. Like, this is cheating as far as I'm concerned. You don't, like, that's not realistic, but it's just way more convenient to go with that for me than trying to properly, like, because like, yeah, I just basically deleted a lot of details. And so anyway, there's going to be another video that's going to cover how load line factors into this, and also, well, the design alterations that can be done to try and improve transient response a bit. But anyway, so this is actually it. So like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And right, if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly. There's a link to that down in the description below. And yeah, that'll, well, that makes it possible for me to make videos like this. And then, of course, more importantly, it allows me to do all of the testing, because it's like the oscilloscope, thank you, Patreon. Well, thank you, patrons, very much for that, right? So, yeah, that's it for the video. Thanks for watching, and goodbye.